so this has worked last time, it doesn't now. Okay. So shadow models, incremental transformations for MPS. MPS is a language workbench, meaning an infrastructure where you build DSLs or other programming languages, or other languages, I should say. And it has, of course, a transformation infrastructure where you can transform more abstract stuff to more concrete stuff, otherwise known as code generation. But it's basically batch. You press Control F9, the build machinery starts running, it generates stuff, and that's sometimes annoying, which is why we've built an infrastructure for doing this incrementally. As you change your model, the transformation runs and maintains incrementally another model that is created by transformation from the input. We have a couple of use cases. Oh yeah, I just changed the slide order, so we start what it is first. It's a functional transformation language. You specify the transformation basically as functions. It's incrementally executed, that's the whole point. It's unidirectional, so we're not trying to synchronize two models in either direction. There's always one model that the user edits and another model that is created from that. However, if you annotate any kind of analysis result to the target model, for example, by running a type checker on it or by running some kind of analysis on it, then we have trace information to pipe the kind of messages annotated to the result from the analysis, pipe that back up to the input model. So in other words, you see the errors in your input even though they're found, the errors are found on the output of your transformation. And this step up here, that's customizable, so you can adapt the error messages so they're meaningful to the input model in terms of the abstractions. And of course, it's fully integrated into MPS, otherwise that would be rather pointless. Of course, the idea is as the user edits, we create basically a delta, a description of what has changed, and that then reruns the transformation for that particular increment and updates the shadow model. Now, the nice thing about MPS in this context is it's a projectional editor, meaning every user interaction is already an event. So we don't have to do like, diffing the old and the new state to find the delta and then run the transformation on that delta. Every user action automatically produces a well-defined difference, and we can directly use that for re-triggering the transformations. And as I said, one major reason why we built this is because we found that many analyses are easily run on some representation of a domain that is different from what the user edits in. And so this notion of piping the transformation or the analysis results back up to the input is crucial. I'm going to show you one more slide and then we're going to the demos. It's a tool demo after all. So we have several use cases. For example, whenever you have some hierarchical instantiation thing, for example, components with nested component instances and connectors, or feature models with nested instances of other feature models, in the context of product lines, many analyses are easier once these hierarchies are flattened. And so one use case is that we run the flattening transformation and we have the big flattened model as the shadow. We can run the analysis there. We have a research project where we used this approach to weave safety concerns into C code, like redundancy or CRC checking. You mark up where you want this thing woven into, and then the transformation does it in real time as you edit the code. You see the transformed code that has the safety checks in it. And then the final example, which I'm going to show live, is basically, one more slide. Basically a functional programming language called kernel F2, which we use for incremental extension for building DSLs in the business domain, various business domains. And here we have two ways of running these programs, of running these models you create using the DSLs. One is we generate code, usually Java. Unfortunately, in the next project, we have to generate C. Of course, the code generation, it's fine if you do it, batch on demand. It's not kind of incremental, immediate user feedback anyway. But we also have an interpreter where users can, as they write their, for example, text calculation code, directly run the test cases immediately, like in the IDE, immediate feedback. And of course, there you want this desugaring to happen incrementally so that you only have to write an interpreter for the core language and not for all the DSLs. So the idea is having a complex language reducing to something simple. The idea is old, and generators have done that forever in MPS, but doing that incrementally in real time so that you can immediately run the interpreter, which is defined for the call language, that is new. So too many words, I'm going to show it to you, and then it's going to become very clear. So here is MPS. What you see on the left side, well, here in the middle, I guess, is a program the user edits. Here on the right side is the result of the incremental transformation. And in this example here, you can see a stupid hello world-like program. It has a bunch of enum, or one enum with a bunch of enum literals, and basically a multi-option decision thing. And on the right, you can see that the core language, this kernel F2 core language, doesn't actually have enums. It only has constants, right? So if we look at the enum color, it is transformed to global constants. And then if I refer to an enum literal here, you actually, in the desugared version, refer to the constant. And of course, now the point is, if I modify things here, the stuff on the right immediately changes, right? Can add this back. Come on. Yellow. So now, of course, everything's fine. But if I make this yellow again, I get an error message because now my enum literals have duplicate names, which is probably not what you want. Point is, there is no check in this language that checks for duplicate enum literals. But there is a check in the core language that checks for duplicate names of top-level declarations. And so because this one triggers that declaration name error, we lift this error here, but you can see it's a different error message, right? So we if you will, semantically lift the low-level error to something that's meaningful in the source domain. You can also see if I, for example, add a bunch of alternatives to my multi-criterion decision, then this is mapped to a bunch of nested if statements, if expressions, I should say, because the core language doesn't have this. So this is already a syntactic extension. Some more examples here. For example, we also have, where are my decision tables? Here. Decision tables, one of the all-time favorite examples in MPS because it demonstrates that you can use non-textual notations. But here the point is that this is incrementally transformed to nested alt expressions, which then is reduced further to nested ifs. This works because the transformation engine supports a fixed point transformation. So it continues to apply transformation rules until nothing is left to do. That is not incremental, right? That runs to completion. So that's basically the first example I wanted to show. Here is a more complicated case. This is based on a project we are currently, or inspired by a project we are currently running, where we built a language for expressing text calculation rules. And there's two things you can probably tell. One, the programs are going to be big because it's text, complicated. The other thing is that the tax law implicitly defines basically a kind of taxonomy. Like they say, the taxable income consists of the income from work and the income from money, what was it called, capital, right? And so it kind of implicitly defines a hierarchy of how you compute stuff. And the DSL we built with our customer is basically a way of specifying these trees that align with the taxonomy given in the law. So in other words, the computation happens basically along this tree. You have values that are kind of inputs, and then you have computations that aggregate upwards. You can see this as a bunch of nested let expressions if you want to think functional program, right? But it has a different notation, and it has lots of specific details about this particular domain. And this, of course, is then transformed into a normal functional program. So if you look on the right, you can see each of these nested items becomes a function. These functions call each other, and those items that have no calculation rule, no formula, no expression, they're inputs, and so they look in basically a data structure that is passed around in the calculation to see which values have been given by the client program. So, and of course, this is updated incrementally as well. However, there is one more thing which we added recently, which is, I'm going to go back to the slides here to tease a little bit. So you all know this, right? It's Excel. And we've been thinking about what people like about Excel. And there are obviously two things. One is the table. Seems like it's like with graphical diagrams, right? The table is more easy to understand than text, supposedly, as long as it's small. But the other thing is the execution model of Excel, right? There is no, an Excel spreadsheet doesn't run. It just is, right? The calculation is implicit in the structure. If you change anything, anywhere, the dependent cells automatically update. So you can see this as an incremental interpreter or reactive, declarative dependency structure, whatever. But the point is, you make a change, things update. And since we already had this incremental transformation engine for the shadow model stuff, we separated the transformation part from the incrementalization part and are now also able to attach basically an interpreter to that incrementalization thingy. And so if you look at this text calculation example, there are a bunch of test cases here. And if I change anything in the test case, then it automatically, immediately fails or succeeds. And of course, this works not just if I change the test case, but it also works if I change anything in the program. I can directly see which test cases fail. And the interesting thing here is that's actually a two-step process going on, because first, this is desugared, shadow model transformed, to the pure program, like on this abstraction level, without any of this syntactic sugar. And then on that, we run the incremental interpreter to update, well, if you will, the execution of the program. And in the end, this gives exactly what we need. In this particular use case, users can write high-level code. They get immediate feedback on the validity of their test cases. And at the same time, this is important, I don't have to write an interpreter for all the extensions. I only write a transformation back to the core language, and from there I have the incremental interpreter and a Java generator. So I avoid the duplication we had before. So that's basically all I had. I have 5 minutes left for questions. I can show the transformation code if you want to see it. So I have that, of course, as well. Yes? Yes, looks like this. So basically, you specify the output as abstract syntax, tree, builder, pattern, nodes, right? We don't use the concrete syntax that MPS uses in some places. And then you basically specify in the headers of rules basically what you do. Like there's, for example, a generic transformation called desugar that takes anything and produces anything. And then you override this here. For example, it takes a calculation object and then produces from a calculation a record declaration and a function, right? So the granularity of the incrementalization are these rules. And then there are a few details about identity management, which are ugly, which we have to improve. And then there is an engine in the background that executes these things. So the syntax isn't perfectly nice yet, but syntax is easy to improve. As soon as we have more experience with this, we might make it nicer. That's the smallest problem in MPS. More questions?
So if you have DSL-specific semantic rules, can you then get incremental?
What do you mean with semantic rules?
When you had an example where you had declared yellow twice.
Oh, you mean the error checking? Yes. Mm-hmm.
Yes.
Sure, you can always define checks for your DSL as well.
And they are incremental also? Or?
Well, they're yes, but not because of us. So MPS already has, they call it the type system and the checking framework, whatever, and that is incremental anyway. So that looks, basically tracks your changes through retracking and then only reevaluates those checks and type checks that are affected by whatever you changed. So yes, but that has been there before.
So you showed before how to lift an error message on the
Yep.
lower level. If you would have a debugger on the lower level language, could you use this to debug on your DSL?
Yeah, could we use it to debug? I just remembered I should repeat the question. Sorry. So in this case, this is a functional language. So debugging doesn't need like stepping. It's enough if you kind of expand the tree of the sub-computations. We haven't so we have a tracer, we call that, for kernel F, for the predecessor language. We haven't done that for this new version, and we have not yet integrated it with the desugaring here, with the shadow models. But all the information we need is there. So we've done, in an earlier project, we've done an integration with GDB for C extensions. And the way we did that was basically that in the place where you define your transformation, you also specify the granularity of stepping, step in, step out, and how you compute watches that are domain specific from the low-level watches of the C level. So we know how to use trace information to rebuild the, let's say, input or higher level abstraction on which you want to debug, but we haven't done it in this case yet.
More questions? So I have a question. Maybe you can start connecting your laptop while so that was about this tracking of errors between between the two programs. Was that, I didn't catch, was that something that's handled by the shadow model, or is that?
Yeah, so what shadow models does is, if there is an error on the target that is created by whatever other means, we don't care, then the shadow models takes the trace information and attaches that same error to all inputs of that rule that produced the node which has the error. However, you can intercept that, and you can say if the error on the target is of this type or of this text string, then kind of ignore it and attach these other errors which you then specify to the top level. So either if you don't do anything, the error messages are just piped up along the trace, at which point they show up at the right nodes, but they're worded in a useless way, which is why you intercept them and create more meaningful error messages. And if the error goes away at the low level, then all at the top level go away as well. So this lifecycle management is automatic, but the semantic transformation, like the wording of the error message, that you have to do manually. But the point is you do it in line with the transformation. It's not like a separate thing where you then forget what you have to do. It's like same place, because that's exactly what it should be. It's the reverse of the transformation semantically. So that's quite nice.